Okay, so today our plan is just to go over midterm. I'm trying to recall that I think I computed the averages. Well, you can see the average for the entire class. Oh, hold on, because you'll this thing. WebEx assistant. Okay. Well, I don't think I had it written down here. Okay. So just for perspective, my LaTeX code here is extremely small. Okay. So just for reference, to give context to your own score that you see in Canvas. All right. So the mean score was for graduate students, 5, and then for undergrads, 75. Well, you look at median also. Okay. The mean, of course, can be skewed. So 97.5 for graduates, and not too much different. Not too different. Okay. All right. So, regardless of your score, unless it happened to be 100, and there were a couple of those among the graduate students. Then you might want to have a clear idea. Besides that, you should be able to see feedback that I left in Canvas. That's included as a comment in the Canvas gradebook. But here we can take a closer look at all these problems and make sure that everyone understands how to do them going forward. Okay. So first would be regular problems. So in this case, we're approximating this function, x to dx, using just 2 interpolation points. So we have n equals 1, the degree of the interpolating polynomial, what's labeled the p1 of x. So the error formula is the following, that f p1 of x is equal to, so we have the second derivative at an unknown point over 2 factorial, which is 2. And then we have x plus 1 and x minus 1. So x minus each of the 2 interpolation points plus minus 1. Okay, now in this case, you use a product rule to take the second derivative. And when you do that, I'll just cut to a chase here, we get t plus 2 e to the c, and then times x squared minus 1. And xc has to be belong to an interval containing the interpolation points, so from -1 to 1. And the problem asks for an upper bound for the error on -1 to 1. So x also confined to this interval. So what you need to do is find the upper bounds on this interval for the second derivative and for this part right here. So But since we have a second derivative up here, you really want to take a look at the third derivative. So that's just going to be x plus 3 e. Stop that. Hold on. Stop. I don't know why I thought I wanted my music app. Sorry about that. Okay. All right. So this function is x e to the x. Anytime you take a derivative, you add one to this polynomial here. So x plus 1, x plus 2, x plus 3. But for x between minus 1 and 1, this is always going to be positive. So f double prime is increasing on the interval minus 1 to 1. So you'll need to check the endpoints. So for this part, to maximize this, all you got to do is set x c equal to 1. All right. So because this function is positive, we want to max absolute value. Then for the other part, x squared minus 1, all right, you take a derivative, it's just 2x. So the critical point is that x equals 0. So you substitute that in here, and you get minus 1. So the absolute, there's no need to check the endpoints in a case like this because the value of the endpoints will always be 0. So the max and absolute value is just 1. So this part can't be bigger than 1. And then here you set x c equal 1 to get the max. So now we can wrap up. And you get 3 times e to the first, so 3e over 2. And that's roughly 4.077. Some mistakes I saw was either this problem or other problems that dealt with polynomial interpolation error. It came up in 3 different problems. Having the wrong value here, like either for a factorial or the order of derivative. So that it's always going to be one more than the degree of the interpolated polynomial. Are there any questions either from people here in the room or the virtual meeting about this one?
You can also do that.
What?
You can do that.
Oh. That's a problem. Oh, okay. Not sure what to make of that. Thanks for letting me know. Okay. So any questions about this one? Okay. Next one, convergence problem. So in this case, you're given that the limit is 1. So for rate of convergence, so you're trying to find the order of magnitude of the function minus the limit. H minus 1, H minus 1. So now if I just make one fraction out of that, so that'd be e to the h minus 1 minus h all over h. So what you need to do now is replace e to the h. So you don't need to do anything with this. This is already a polynomial in h. So a non-polynomial h, just that part, you can replace with a Taylor expansion. So that would give 1 plus h plus h squared over 2. And then there are more terms, of course. So those, whatever terms that follow would be order h cubed. So really you want to put in enough terms so that you can simplify the expression as much as possible. What we see here is that the first two terms, the 1 and the h, will cancel with a minus 1 and minus h here. So that everything else sticks around and is divided by h. So what you get is 1/2 h plus something that is order h squared. Now, h is going to 0, so it's the smallest power of h that determines the rate of convergence. So it's this order h in this case. Questions on this one? Okay, next we have a catastrophic cancellation problem to resolve. So, there's a couple problems, but really only one that can be readily taken care of. Because if x is, for instance, slightly greater than 1 in absolute value, then we can have a cancellation error in this case. The subtraction itself is actually very easy to perform because all you're doing is subtracting 1. The result of this is just going to be the digits in the mantissa of x squared, except if x is very close to 1, there's still a loss of precision involved. Unfortunately, the techniques that we've seen in class for working around that would not immediately be helpful in dealing with this. But there's another cancellation issue that can be dealt with, and that's with this subtraction right here. So for large values of x, because here in this radical you're adding 1, this radical you're subtracting 1, but taking the square root of both. As x gets larger, adding and subtracting 1 makes less of a difference in the result. So these numbers, as x gets larger, are actually getting closer together. So what you can do is, as what's been helpful in other problems, is multiply and divide by the conjugate. And once you simplify all this by multiplying out the numerator, so we have x squared plus 1 minus x squared minus 1, the x squareds cancel, and you're left with just 2 up top. So this problematic subtraction became an addition. Questions on this one? All right, here we have Lagrange interpolation and also dealing with the error. Here we have 3 interpolation points, so the interpolant will be quadratic. Okay, so what we get for the Lagrange form, let's write it in the unsimplified form. So we'd have cosh of -1, the first coefficient, and then the first Lagrange polynomial would be x minus the other interpolation points. So that's the first term. Then you have cosh of 0, which is 1, times the second Lagrange polynomial, so that's x plus 1, x minus 1. We have 0 plus 1, 0 minus 1. So x minus the other points, 0 minus 0 points. This term is for the interpolation point -1. This term is for the interpolation point of 0. And then finally we have third term corresponding to x2 equals 1. So we want the value of the function at 1. And then we have x minus each of the other interpolation points, -1, 0. And then, okay. So in its unsimplified form, this is Lagrange interpolating polynomial. Next, the error. So n equals 2. It's quadratic. So we have. All right. So now we have the third derivative at an unknown point. Over 3 factorial. Times, so plus 1, 0, minus 1. Okay. Now, we want the error, the bound on the error at 0.25. And I feel it should have been clear, using the error formula, not simply computing the actual error at 0.25, for which I gave partial credit. Now, the value of x being 0.25 is only substituted in here. This point is unknown. The only thing we know about it is that it lies in the interval containing the interpolation points, so it's between -1 and 1. So x is 0.25. And c is some point in -1 to 1. Also, the third derivative. So if you take a derivative of cosh and you get sinh, and then you take a derivative of sinh and you get cosh, and this goes back and forth. So odd order derivative is sinh. Now if we look at the error at 0.25, so we're going to have, well, sinh is an increasing function. the derivative of sinh is cos, which is always positive. So what we have here is sinh of 1. So I'll make a note here, always increasing. Okay. So sinh 1 over 6. And then we substitute 0.25 here. Okay. So then once all of this is worked out, what we get is a few decimal places, 0.459. What some people do is so we assume that sinh is less than or equal to 1. Like the same bound that applies to sine and cosine does not apply to hyperbolic sine and cosine. Sinh of 1 is actually a little bit greater than 1. And this fraction works out to be minus 15 over 16. Oh wait, not 15 over 16. That's wrong. Sorry, I got it confused with a different problem. This fraction works out to be minus 15 over 64. But this is still correct. Okay. Questions on this one? This one is due to interpolation, so we have 4 interpolation points for generating a cubic polynomial from a divided difference table. So in this case, we're going to have 5 columns altogether. So in the first column, I'll put the x values. Okay. All right. So I have the x values 0, 1, 2, and 3. So then, when we substitute all these into sine pi x over 2, I chose this function so that those values would work out nicely. What we would get is 0, then sine pi over 2 would be 1, and then we have 0, and then minus 1. Okay. So now from here we can compute the first order divided differences. So we have this minus this divided by this minus this. So neighboring y values divided by neighboring x values. So the first one would be 1. Okay. And then 0 minus 1 over 1. So that would be minus 1 is the next one. And then minus 1 minus 0 over 1, so that would be minus 1 also. next we do the second order divided differences. So -1 divided by, so 2 minus 0. So remember, you go back to the divided difference table and define these x values. Whatever x values led to these divided differences in the first place, you take the extremal ones. So -1 divided by 2 gives us -1. -1. Okay. And then here we have, here the y values are matching, so that divided difference is going to be 0. Okay. And then finally, we have 0 minus -1 divided by the difference of the last and first x values. So, so we get 1/3 for the final divided difference. So then you can read across like the top row. You write out the polynomial. So the first divided difference is just a constant term, so it'd be 0. And then 1 times x minus 0. And then we have -1 times x minus 0 times x minus 1. And then plus 1/3. 0, x minus 1, x minus 2. So it can be simplified quite a bit. I'm just showing where all the different parts come from in relation to the divided difference table. Questions about the Newton form before looking at the error? Because we have a cubic, all right, so now we have the fourth derivative at an unknown point over 4 factorial, and x minus 1, x minus 2, x minus 3. Now x in this case is 0.5. We can substitute that in here. And then we have now c is the unknown point that lies between 0 and 3. But it's the fourth derivative of sine. We can certainly compute that. That's going to be, so the function is sine pi over 2 times x. So 4 factorial is 24, and then we have pi over 2 raised to the 4th power times sine pi x c over 2. But x c can be any point between 0 and 3. So this we can bound by 1. And then okay, so this part right here, works out to be minus 15 over 16. Once you take all of this into account, have 5 to the 4th, and then I have 15 in the numerator over, so we have 2 to the 4th, so 16, 24, 16 again. And that's roughly 237. So not that great an approximation. I had an error here somewhere. Okay. All right. I've come to the end of the regular problems. So, we'll to answer any questions about those before talking about the lightning round or concept checkpoint. I guess given the time frame for the test, lightning round probably wasn't very lightning roundy, but. Okay. All right, absolute error versus relative error. When is absolute error preferable? The exact value is near 0. So in that case, relative error is skewed to be overly large. We give a not very informative indication of accuracy. How are forward error and backward error related? By the condition number. If we have, effectively how the condition number is defined, but if you have estimate a forward error, which is difficult to estimate directly, you can estimate backward error and multiply by any estimate you can get of the condition number, which can come from a derivative. All right. Underflow versus machine precision. So underflow is based on the exponent range. So if a real number, has a magnitude based in terms of being power of the base, where the exponent is less than capital L, the lower end of the exponent range, then you have underflow. While machine precision, which can be defined as the smallest number that you can add to 1 and still get a result that's considered greater than 1 in the floating point system, based on the number of digits in the mantissa. So two entirely different components of the floating point number are responsible for determining either underflow or the limits of machine precision. most troublesome issues. There are a lot of things that can go wrong in floating point arithmetic. But worst, catastrophic cancellation and overflow. These two, because unlike other issues, such as, for example, not following arithmetic laws or simple loss of precision, at least you still have a meaningful result in those cases, even if it might not be as accurate as you would like. But not in these cases. You can have a result that is almost completely erroneous in catastrophic cancellation. Overflow, no result at all. Numbers too large and is considered infinity. What are you going to do with that? In both cases, resolution, same general type resolution, even though the approach might be different. I wouldn't say this is always possible, but we're writing the expression, as was done in one of the problems earlier in this test for a cancellation error, or one of the homework problems. We write the expression to remove overflow, an intermediate result. Data matrix. So what it's used for here is obtain the coefficients in power form of the interpolating polynomial, because you can set up a system of equations from requirements of your polynomial that when you substitute in a certain x, you must get corresponding y value, and you get a system of linear equations, and the matrix of that system is a van der Waals matrix. The drawbacks, it's expensive to compute the coefficients in this manner, or n-cubed operations, or degree n polynomial, whereas if you use either Lagrange interpolation or Newton interpolation, you get the coefficients, you get the whole polynomial or n squared operations. So the whole order of magnitude can be shaved off. Also, if the x values are close together, then the van der Waals matrix is ill conditioned. Okay. Next. The given 3 points. So lowest degree of polynomial is guaranteed to fit any 3 points you might give. Is the number of points minus 1. I mean, if a points, for example, happen to be collinear, then yes, you could find a degree 1 polynomial that fits them. But the 3 arbitrary points, if the polynomial is degree 2, it certainly will fit all 3. And it is unique because if a van der Waals matrix is invertible, if the 3x values are distinct. You can see this questions 7 and 8 are followed 8 and 9 are two sides of the same coin. So first I'll do number 7. All right, Lagrange polynomials. What are properties they have that make them useful for interpolation? What are about her values at the interpolation points? So it's equal to 1 j, and 0 otherwise. So because they have such a simple expression at the interpolation points, that makes it easy to get the interpolated polynomial in Lagrange form. Which, so the consequence of that is, of the Lagrange form of the interpolated polynomial p of x, so just the y values. That's why they're particularly nice for interpolation. And that'll come in handy in the next chapter, chapter 9, where we use polynomial interpolation to come up with methods for approximating derivatives and integrals. Now, as for a drawback, it's difficult to add interpolation points. So the Lagrange polynomials need to be recomputed in that case. So another way of putting it, it is not a progressive interpolation method. Which actually is also the answer to number 9. I was really thinking there when I was putting questions in these sections. So Newton's method, Newton interpolation, is very different from Newton's method, is progressive. So adding new interpolation points is to just one new term, and all the previous terms, you can keep those. So really what you're doing is you're just adding one more row to your divide difference table, and reusing all the work that you had before. And lastly, high degree polynomial interpolation. What happens, the error gets very large, as illustrated in the Runge's example. Especially with equally spaced points. Actually, Runge's example is about that. So both issues, high degree and equally spaced points. What you can do to prove a situation, use Chebyshev points. Right, so I guess close as you come to an optimal set of interpolation points for the general case. Okay. Made it to the end. So questions on any of these? From a virtual peanut gallery. Or questions on homework problems. Yes.
Yes. So homework 2.
Homework 2. The error analysis section.
Yep.
Okay. Okay. I'm going to unshare and reshare. Hold on. Okay.
so question 2.1.9.
219.
Yeah.
Okay, well, what about it?
I don't seem to understand the whole question.
I couldn't figure it out.
It's a bit confusing, yeah.
Okay. So we're doing relative error. All right, so you're given relative backward error, 10 minus 2. And the goal is to get an estimate of relative forward error. So for that, you would use the relative condition number. And so the way to estimate the relative condition number is from this. So you would use this with each function at a specified point to get the condition number. So from there, that'll give you your relative forward error estimate. So that's the first part. You do this for both F and G. Hold on. Stop certain notification. Okay. Well, first question's about just that part of it. Does that make sense?
Yeah.
Okay. For the second part, because that's only an error estimate. So suppose you, so to see if that estimate is valid, keep in mind that with backward error analysis, that the approximation to F is the exact solution to a nearby problem. So what that would mean is, in this case, substituting in a nearby value of X. So, so if you take an X value that is this far away from 2, in a relative sense. So pick an X value that satisfies this. And then you substitute that into F and G and find out what the actual error is. Like, so if you pick an X naught hat, and then X naught, and substitute those into F, what does the relative forward error turn out to be? And then that should be in the ballpark, at least, of your relative forward error estimate. And if it's way off, then that would be wrong. Okay. All right.
Thank you.
Yep. Okay. All right.
I have a question about homework 3.
Okay.
If we're working in a system of where floating point arithmetic with base 10,
Right.
suppose we have like, I don't know, like 2 significant digits. Are those digits 9 and 9?
Oh, wait, okay. Oh, you mean like it's part of your mantissa?
Right, what's the highest mantissa in base 10?
Oh, okay, so, yeah, so the highest mantissa you can have is like 9.999.
Okay.
Yeah.
Until wherever.
Yeah. Where the total number of digits is your precision P.
Right, and in base 2 is it 1.1111?
Right.
Okay.
So
Yeah.
basically whatever it allows, depending
Yes.
on the space.
Yep. Yeah, you have the highest possible digit in each position. Okay, so I'm going to amount of time. Any other?
I might have another. Okay.
Not at the moment, but I have some others, so I have to make a list.
Okay.
Can I ask about one of the concept check questions?
Yep.
It went away. Actually, maybe it's not a concept. No, it's actually homework 4.
Oh, okay.
Sorry about that. 7.1 exploration 3.
Okay.
The first thing that occurred to me, I think, will only guarantee that the two functions are equal at the interpolation points, but we need a proof that shows that they're equal even between the two, right?
That's right.
Okay, so am I on the right track if I'm considering induction?
Because it can definitely be done without induction. So I'm not sure if it would help. If now, that said, it might. In many proofs like this one, it could be that if you use induction not so much to write out the final proof, but to give yourself an idea as to why it's true. Because really, any problem involving a proof is a matter of first convincing yourself the result is true, and then writing it up from there to convince me that he knows it's true. So working with some base cases might help you see why it has to work out that way. Since I know it can be done without an inductive argument, it's something that might turn out to be more complex than necessary.
Okay, thank you.
I guess a way to think about it is, if I just had any two functions, and the only thing I knew about these functions were that they happen to agree with each other at these n+1 points, then yes, I definitely could not conclude that they're equal in between. The fact that they're polynomials of a certain degree is what matters.
Okay, thank you.
I have a question about 2.2.8.
228.
So it says do not assume that d sub 0 equals does not equal 0.
Right.
Does that mean 0.0001 can be an antissa?
Yeah, it's allowed.
Okay.
Another way of putting it is a number is not normalized. Which sets up one of the later problems.
Right, it's a normal. Okay, yeah.
Alright.
Also, do we have to prove 221?
221.
Or just show the example and then generalize that?
Yeah, I'm fine with that.
Okay.
We have a course, Math 772, which required for PhD students. It's also numerical analysis, but more theoretical. In fact, the textbook is literally called Theoretical Numerical Analysis. Dr. Tian teaches it every spring. I don't know how theoretical she makes it, but numerical analysis is a funny subject that way, that it's possible to have a class on numerical analysis that doesn't really have any proofs at all and just deals with more of the coding aspects, or it's possible to have a class on a subject that has so many difficult proofs that would make you wish you were taking real analysis. I shoot for something in between, but. So we have 15 minutes or so. Checking out the chat, nothing there either. Okay. Oh wait, there's something in the chat. Oh, okay. One more comment I want to make, although, because I noticed that in every class we have a handful of people here in the room, and then we have a handful of people in the virtual meeting that definitely does not add up to anywhere near the 21 students who are still enrolled in the class, and all but one of those, so 20 students altogether, took the midterm. And my assumption has been that anyone who doesn't show up live in any capacity is at least watching the video later. But my concern is that there are some students, I mean, we have some who are doing extremely well, both on the graduate and undergraduate side. And we also have some students on the undergraduate side who, from what I can tell, simply are not as tuned in to the material as they should be. I try to put a lot of resources out there besides whatever I do here during class, and not just the textbook, but also to be able to, answering questions that come my way, and also the practice midterm solution, which I could tell were not viewed by some students, and that just simply isn't a recipe for success in this class, or really any class. It's very important to tune in, and not everyone is doing that. And I hope that if the test did not go so well for you, and unfortunately it does count for 30% of the grade, but there's still a lot of your grade left to be determined, and I hope you'll keep this in mind going forward, that it's very important to take advantage of the resources that I put out there, and then also whatever guidance I can provide, then you'll be on a much more constructive path. So please keep this in mind, everyone, for the remainder of the semester. Okay, so of course Thursday's first day of fall break, so we won't have class then. So those of you who tend to show up, I'll see you in some sense on Tuesday, and I hope that everyone else will see me by watching the video later. Okay.